Hello, CHistrue, and this is a video done by special request, and that is how one can figure out the distance between the Earth and the Moon, knowing some things that we know today that were not known in the time of Aristarchus. And I have here how Aristarchus actually did it. I'm going to post it below. It's kind of cool. It has you use the shadow of the Earth on the Moon. And that's one possible way you can do it. But in order to replicate that, you'd have to go out during an eclipse and measure all that. And since CHistrue, I'm lazy, gone lazy these days, I'm just going to do it mathematically, knowing some things that Aristarchus did not know at the time, one of those being the gravitational constant, uppercase G, the other being the mass of the Earth. We don't need to know the mass of the Moon. We do not need to know the mass of the Moon. We're going to make some assumptions. One of those is we're going to ignore the influence of the Moon's gravity on the Earth, such that the center of motion of the whole system is not exactly the center of the Earth, but we can neglect that. We're going to neglect the gravitational influence of the Sun, some differences. Basically, we're neglecting the entire issue of the fact that the orbit of the Moon around the Earth is not a perfect circle. So we're going to make some assumptions here, and this is the assumption we're going to make. You can freeze that and copy it down, but you see that the centrifugal force and the centripetal force, they have to balance. D would be the distance, and I'm putting it from the center of the Earth to where the Moon's orbit is, and we're assuming a circular orbit. It's not to scale. We're going to see how close we can get with this. This is centrifugal force, m times velocity of the Moon squared over the distance between Earth and Moon. However one would figure that, slight variations. And that's equal to the force of gravity on the Moon, which is gravitational constant times the mass of the Earth times the mass of the Moon over d squared. Okay, so we're going to see how close we can get to how far away modern astronomers estimate it using probably the same, more or less the same method. Aristarchus got pretty close, by the way. Aristarchus, I'm going to post his method down there in the box. I'm going to link to it. It's a good method, and yeah, you can definitely use his method if you want to verify this answer that we're going to get. And this answer, by the way, is very, very close to the official answer. So this is a special request. I'm a little green, so if I stumble over my words, I apologize in advance. Okay, so we now have, I might have to put it down here. We now have our formula that we had, so you'll have to scroll back to the other page there. Let's see how much time we have. Plenty. Okay, and so what we do is we figure out that the velocity of the Moon is 2 times pi times the distance between Earth and Moon over t. Now t is going to be, in this instance, we're going to use meters and seconds. So we're going to calculate it, d in meters, and then convert it to miles. T is going to be in seconds. So how many seconds are in one lunar month? Well, we'll figure that a little ways down the road. But if I plug this v back into... Oh, by the way, I canceled one of the d's down here. This is just g times uppercase m times lowercase m over d is equal to mv squared. So I just canceled on 1 over d on both sides. Plug this v over here, square it, and I get 4 pi squared d squared over t squared. Hope you can see that. Okay. And this lowercase m is the mass of the Moon. Obviously that cancels. So that's a very important thing to know, is that the mass of the Moon doesn't matter in this. That distance for a period of orbit of 1 month, you could have a tennis ball out there. Now again, we're ignoring gravitational influence, the fact that the Earth and Moon has a common gravitational center a little ways off. But you'll see that well, I'm not going to give it away. We'll see if we get the answer. We'll see if we get a good answer. If we get a pretty close answer, that means we can ignore it pretty well. So I won't spoil the surprise. A little bit of algebraic reorientation here. Bring the t... It's 1 over, multiply both sides by t squared, and then multiply both sides by d, And I get G, mass of the Earth, times the number of seconds in a month squared over 4 pi squared is equal to D cubed. And here we have G, gravitational constant, maybe I can put it up here, is equal to 6.67 times 10 to the negative 11. That's an 11 there, but it's negative 11. Mass of the Earth is 5.972 times 10 to the 24th. And then we calculated the number of seconds in a month, and we got 2.36 times 10 to the 6 seconds in a month. So let's pause here for a minute. I've just made, again, a bunch of assumptions that Aristarchus didn't... Aristarchus, that's an anglicization of his name, that he did not have at the time, and yet the brilliant astronomer that he was able to get pretty close. Let's see if thousands of years later, if CH is true, sitting in an easy chair gets even closer, or anywhere near as close. Okay, so D cubed is equal to, we multiply all these together. And this, by the way, is T squared, so 2.36 times 10 to the 6, you square it, and get about approximately 5.5. I lost significant figures here because it's an approximation. So already, we're getting into approximation land. 5.5 times 10 to the 12th. And there's a reason that I did that is because it's going to be such an approximation given all those other things that I don't really want to make this sound like it's going to be too precise. So I maybe should have done that up above, but I went ahead and did it here. It's not exactly proper, but it's holiday break, so he cut me a little slack here. D cubed is equal to, this amounts to being 5.6 times 10 to the 25. So D cubed is equal to 5.6 times 10 to the 25, and we'll call that meters cubed. But we don't really want that. We want the cube root of that. And so the cube root of that would be 3.83 times 10 to the 8th meters. 1 mile is 1,609.34. Hello, wake up, CH is true. Meters. So when we divide that, we get 237,920 miles, which is very close to the official answer of 238,900 miles. So I think we did okay. Now, mind you, we're ignoring the elliptical nature of the moon's orbit. We're ignoring the fact that they didn't know about that stuff, gravitational constant, and a lot of other things back in the day. So I think we did pretty well, folks. This is CHistrue, fulfilling a special request, signing off.